Let me quickly introduce myself. I'm a professor at ETH Zurich. I'm currently on sabbatical at Stanford, so I traveled here. I'm jet-lagged quite a bit. I traveled from San Francisco. So I have previously to ETH, I was at Carnegie Mellon. Before that, I was at Microsoft Research, and I worked at VMware, Intel, AMD, Google over the course of my career. I did my PhD at UT Austin, undergraduate degrees at Michigan. And I work in computer architecture, systems, hardware security, and bioinformatics. You'll see a good collection of a lot of these things in this lecture with a focus on memory systems, but we'll talk about that. My interests are quite varied. I work on a lot of things. I'm quite interested in many different ideas in general in computing, but also outside computing. Okay, very quickly I'll introduce my research group and what we do, and then we'll jump into some basics today. Today is going to be more of an overview, and then we'll go into more detail in the next 4 lectures. So this is my research group. We do a lot of work on many things. If you're interested, you can read our newsletters. In fact, we recently released a July newsletter a few days ago. So if you want to know what we've been up to in the last year, you can take a look at that. And we have some videos online talking about our research, and we have a bunch of PhD and postdoc alumni who are doing a lot of good work out there. And I have a lot of interviews online, so you can find more information, but you can talk to me also. So what do? We actually are interested in building fundamentally better computers, so hopefully it'll be clear during these lectures. So as I said, we work a lot on computer architecture, hardware, software, co-design, bioinformatics, and security, and you'll see examples of that. This is a very busy slide, including some of the research that we do, but we really work across the stack. And I think in these lectures, hopefully it'll be clear why that is the case. And I should also say that I have a lot of slides. I can speak very fast. If you want to stop me, ask questions. So I try to practice what I preach. Like we're going to talk about fast memory, high bandwidth memory. I think high bandwidth interaction is also important as humans progress, right? That's important. But don't focus too much on reading what's on the slides. All of these slides are available, as I will show you. You'll be able to find the recording, etc. later on. Focus on what we say, what we discuss, the gist of what I tell you. Okay, so we have 5 major current directions that we're pursuing, and you'll see all of these in this course. How do we build fundamentally robust architectures, reliable, secure, safe architectures? I think this is critically important going into the future. How do we build fundamentally energy efficient and sustainable architectures? And that's part of what this course is about, memory-centric architectures. How do we build low latency and predictable architectures? Unfortunately, we're not going to talk about that. We're going to talk especially about these two. But also, how do we build fundamentally intelligent and evolving architectures? Architectures that can learn from their actions over time and get better. And here we're going to look at machine learning assistants and data-driven architectures and data-aware architectures. Let's see how much we can cover. And of course, like everybody should be doing, in my opinion, specialization is very important. How do we build architectures for important workloads? Not just machine learning. There are machine learning workloads that are important, but that's not the whole world. And after this machine learning hype reduces, there will be many, many more important workloads in the world that's going to be important. So keep that in mind. We're not just machine learning agents, let's say, that are trying to improve machine learning. Okay, I'd be happy to talk about those things also. Okay, so this is the transformation hierarchy. You're going to see that later on also, but essentially the way I think of computer architecture is not like this. This is a narrow view of computer architecture. You look at the software and hardware interface and microarchitecture. We'll take a much more expanded view of architecture, which really covers all the way from algorithms to devices. So we're going to talk, in this particular course, we're going to talk about kind of guts of the circuits, focusing on DRAM and non-volatile memory, for example. And also we're going to talk about algorithms that can take advantage of those circuits at the bottom. How can you modify the circuit so that you can take advantage of them for algorithms? So the axiom will be, if you really want to achieve the highest efficiency, performance, robustness, and I believe security as well, we really must take this expanded view of computer architecture and really co-design our systems across the hierarchy from algorithms to devices and specialize as much as possible within the design goals that we dictate, as we will discuss. Okay, I'm just giving you an overview of my philosophy right now. We still haven't started the, let's say, the technical part of the lecture. But I really believe in what's written over here. That's one of the reasons I teach this course, and I enjoy teaching courses in general. I think teaching and research are two sides of the same coin. Research is all about figuring out something that no one has figured out, and then educating the community. Teaching is all about telling or educating the community about something that everybody can figure out, right? It's just the differences in research. You figure out something that no one has known before. And I think this is a kind of a loop, if you will. This is my PowerPoint animation of the loop, basically. They kind of snowball each other. They help each other. Okay, I also believe a lot in open sourcing, so we open source a lot in our research. Almost everything that I discuss in this course is open source, so this is actually good for people like you who may be interested in research topics, and it's relatively easy to start. In fact, maybe toward the end of this lecture, or maybe tomorrow, I'll give you an assignment on one of the open source things, but you don't have to do it. I'm not going to grade your assignments. But you can talk to me about it. And I'm going to reference a lot of papers, etc., and they're going to be all online. You can find them on my webpage. We put a lot of material, lectures. In fact, you may have seen some of the previous versions of the lectures. I change all my lectures, so there's always some updated material. It's all online. Let me give you a quick course overview. This is the aggressive agenda. This is the compile time static agenda. Dynamically, we can change it. And I believe in dynamic systems. Compile time usually cannot adapt to dynamic interactions, right? Whereas dynamically, we may change this. So our goal is to cover today topic 1, memory trends, challenges, and opportunities. I'm not sure about covering basics. We will see, since many of the... Okay, maybe I should get a show of hands. How many people here are PhD students? Okay, quite a few. How many people here are master's students? Okay, that's good. How many people are bachelor students? Okay, high school students? Okay, not yet. What about researchers or faculty? Okay, none of the above. Okay. Okay, that's good. Yeah, that's a good distribution, as I expected. It was like that similar last time. So you will, a lot of you are quite advanced, so I'm going to not talk about a lot of detail on a lot of the concepts, but feel free to ask me questions if you want more detail. Okay, tomorrow I hope to cover memory-centric computing. It may take multiple lectures or multiple pieces of lectures, and then we're going to talk about memory robustness, and then hopefully, if time permits, we're going to talk about using machine learning to drive the design of memory systems. This doesn't mean that this is all the topics that are important. For another course, we could have architectures for genomics, for example, which we will briefly talk about. And then there's a lot more on memory also that we're not going to cover, unfortunately, because there's just not enough time. Like in an earlier version, in 2013, when I taught here, I talked about non-volatile memories. But we don't have time this time. In earlier versions, I talked about memory latency, predictability, quality of service. Again, those got dropped because other things became potentially more interesting and more important. And we have a bunch of overview readings. You may have seen that in the course description. All of the links are here. And this is the course website. How many people visited the course website? I put this up website, but also there's a HiPEAC website, I think. I will try to update it. I tried to upload the latest version of the slides yesterday, but the internet was so terrible that I couldn't upload anything. I think it stopped at 11% of the size of the file. Okay. This is my contact information. If you want to contact me, email is good. WhatsApp is actually even better if you're here. You can find me during the breaks, and we can discuss. And if you're curious about what we covered in 2013 and 2018, we have websites for those also, and we have videos. This time we have a professional videographer, so the videos will be much better this time. Okay, so this course, what will we cover? Essentially, we'll cover many problems and solutions, or potential solutions, related to the design of memory systems and memory-centric computers. This is really important because the design of the memory system and memory-centric computers poses many challenges. Difficult research as well as engineering and implementation problems. Important fundamental problems. These are not easy problems to solve, otherwise they would have been solved by now, in my opinion. And very industry relevant problems. Industry is actually grappling with this quite a bit, and unfortunately because of the processor-centric paradigm that we've been used to for more than 80 years, they cannot get out of that paradigm, and we will discuss that also. But whatever you do in this area can have huge impact, as we will see with some examples. And in my opinion, we're going to cover problems whose solutions can actually revolutionize the world by changing the computing paradigm as we know it. And I think one of the reasons I like working in this type of area is you can come up with many creative and insightful solutions to these problems if you think out of the box a little bit. So what is my goal in this course to get across? I hope you will acquire the basics to develop such solutions, because basics require you to understand the field a little bit, and this course is intended to give you an overview of the field. What are the problems in the field and what you can do? What are the tools you can use to improve the field? We'll cover fundamentals as well as cutting edge research, and I think these go hand in hand. Some of the cutting edge research is actually in solving the fundamental problems. Does that sound good? Okay, I see nods. So how do you make the best out of the course? I would suggest following the lectures, being alert. As I said, they will be fast-paced. Do the readings as much as possible. I know you have a lot on your plate during this time. If you do the readings, they will supplement the lecture, and you'll really understand a paper much better if you actually do the readings. And I will provide many references. I will not go into a lot of methodology, for example, in some of the papers, so you should really do the readings to understand the methodology. And methodology is usually very important to evaluate ideas, as you probably know. Going back to the fundamentals and reinforcing them could help. I will provide a lot of pointers to that also, as you will see in a little bit. And always remember Pasteur's beautiful quote over here. Chance favors the prepared mind. There's always such a thing as chance, and there's always such a thing as random chance, but if you're prepared, you're more likely to be lucky, let's say. So I think you're doing the first step right, meaning by attending these courses, because you're helping your preparation, right? Okay, so as I said, unfortunately there's no time for a lot of topics related to memory. If you're interested, you can find these in our more basic courses. So if you want some basic materials in computer architecture, this is the course I would recommend. This is the spring 2023 incarnation of the digital design and computer architecture course that I teach at ETH. It covers a lot of basic material, but also a relatively advanced material also. And if you want more advanced material, some of which we're not going to cover in this course, this is the computer architecture course at ETH. And I like the fall 2021 incarnation if you're interested. And this is one of the papers that we're going to cover. We were supposed to update this paper to become more than 150 pages or so, but it's not updated yet. I'm going to mention this later on. And these are some of the other papers that are going to cover some of the material. No paper covers every material, or no paper or no book covers everything that we're going to discuss in this course. At some point I should write a book, but we're not, I don't have time for that yet. Okay, any questions on whatever we covered so far? No? Okay, then what I would like to do next is to give you an overview of what our computing platforms are like today, so that we can discuss what we want from future platforms. This is going to be more fun. You can relax a little bit. We're not going to cover the technical material directly, but I think this is a really important exercise to do, because this really sets the stage of what we're doing not so well in our computing platforms. So I will start with the question, why do we do computing? Anybody has an answer? What's the reason, right? We should just go back home and sit and not do computing at all. And in some ways it may be better. Well, maybe I'll answer. That's to solve problems, right? We have a lot of problems, and I think the reason we do computing is to solve problems. If you extend the answer, or reword the answer, to gain insight so that we can solve the problems. And I would recommend Richard Hamming. How many people know about Richard Hamming here? Dick Hamming. Hamming codes, error correction codes, that's good. Yeah, he has beautiful books and beautiful philosophy about computing. He basically says, at the time he was doing his research, a lot of people were doing computing for number crunching, just to get results, right? And he basically said, our goal is not to just get results. Our goal is really to make sense of those results. So the reason we do computing, we design computers to gain insight, and the results are just a means to get to that insight. And I strongly believe that. That's why I think insight is really important to focus on. If you extend this answer, we do computing to enable a better life and future for everyone, right? And It has had successes, but it's not clear if it'll have those successes going into the future, because there are aspects of computing that are actually making our lives worse as well, not just psychologically, but also in terms of climate, sustainability, etc. So we're going to talk about that in the next lecture. Okay, so given that we want to solve problems, how does a computer solve problems? So we have, and the answer, well, I should have asked probably, but in today's dominant technologies, computers solve problems by orchestrating electrons, right? Now, this is not an easy task. It would be nice if I could orchestrate electrons by telling electrons, electron, do this for me, right? Unfortunately, that doesn't work. At least we don't know. We haven't figured out how to make that work yet. So what we do is we come up with a transformation hierarchy that starts with some problem that we want to solve. It could be some machine learning. It could be some, I don't know, search for some information, right? And then we need to bridge the gap, because we cannot just speak electron language. To bridge the gap, we specify the problem in terms of an algorithm, and then express it in languages, and then execute it on some system software and hardware combination, and communicate that those instructions in the program using a instruction set architecture or software hardware interface, depending on what your software hardware interface is. It's different in different kind of machines, right? And then that gets implemented using some microarchitecture constructs, which gets implemented using logic gates, which gets implemented using devices which operate based on electrical physics principles, right? And this is a transformation hierarchy that has been very successful, as we have seen. Now, if this was a more fundamental course, I would actually go and define every single thing over there, but you need to read, you need to go through the digital design and computer architecture course for that. But I'd be happy to talk. So the narrow view of computer architecture has a long time been the hardware-software interface and the microarchitecture. In this course, as I said, we're going to take an expanded view, and you will see examples of this a lot. Okay, so what is computer architecture? I'll define some basics. It's really the science and art of designing computing platforms. And given this expanded view, it's not just the hardware, it's not just the interface, but it's also the system software, programming model, and the co-design across the hierarchy. And I should emphasize art over there, because art is also important, because it's not a complete science, in my opinion. It's very difficult to make it complete science. And one of the reasons is we're really designing computers for the future, right? We're not designing computers for the workloads that we know today. These computers will run 10 years down the road, and how can you predict 10 years down the road? How can you actually optimize in a scientific manner what is going to execute on this computer 10 years down the road? Essentially, you don't, because you cannot do that. So you really need to go into the artistic or architectural concepts also. That's why it's called architecture as well, in a sense. So what is essentially, we design computers to achieve a set of design goals. It could be the highest performance on Earth on some workloads. It could be the longest battery life at a form factor that fits in your pocket with cost less than some amount. That's mobile computing, for example. Or it could be the best average performance across all known workloads at some performance cost ratio. That's more general purpose computing, right? The first one is more supercomputing type of applications. But you can expand this. Clearly, there are many, many use cases over here. I'll show you some examples. Designing a supercomputer is different from designing a smartphone in the end, but many fundamental principles are similar. And hopefully in this course you will see that especially the memory system is so fundamental to all of the computers, and it's very similar across all of these systems. And maybe we need to change that going into the future. Okay, so let me show you some examples very quickly. These are some things that you may be familiar with. These are all different platforms that operate for different goals, and they have different constraints as well. I like this one because this is Mr. Bean envisioning self-driving cars a long time ago. How many people watched that? Okay, if you watched that, that's good. Yeah. So you can empathize with that. We're going to get back to this one. Okay, this is a real self-driving car a long time ago, maybe 15 years ago. You can see the computing infrastructure in the back. Genome analysis, we're going to talk about. This is an example system in your pocket. This is a data center, which looks similar to the supercomputer, although they're very different in terms of what they optimize for. This is another supercomputer, one of the fastest. This is a machine learning accelerator, an example. Another example, I cannot keep up with these machine learning accelerators, so I'm going to leave it there. This is another machine learning accelerator designed for a specific purpose, for self-driving. And I like to emphasize this one because they have a beautiful talk on YouTube. They don't design just a chip to do the training and inference of machine learning, but they actually design the entire system and this is one of the slides that they use in the talk. Chip is part of it, but you really need to design the software, cluster, system, and chip so that you can do the training based on the data that's coming from many, many different cars, right? Okay, this is a GPU, which you may have used. This is another type of machine learning accelerator that people are building. This is essentially a chip that's this big. It's a wafer scale chip. How many people heard of this? This is the Cerebras company, yes. So people want to put compute, large amounts of compute and large amounts of memory together at low latency communication, and that's the reason they're building these chips. They're really trying to solve the problem of accessing data at low latency and high bandwidth. And they have a lot of data on this chip, but it's not enough. Maybe they have 80 gigabytes, and 80 gigabytes is very, very small in today's standards. Okay, we're going to get back to that also. And there are many other machine learning chips. Kunle talked about his chip yesterday. I'm going to talk about that maybe at some point. So this is clearly interesting. Now these are some different things. So if I was teaching this course well, I did teach this course in 2018, and none of these were there. Well, some of the other ones earlier was not there, but this is a processing in memory chip that this company in France, UpMem, designed, and we've been doing a lot of experiments with it. So you can actually do experiments with processing near memory chips today. So you're lucky right now taking this course in 2024 as opposed to 2018. So we're going to have a lot of updated material. So these are real. You can actually offload some workloads, and we have papers on that. I'm going to talk about that later on. This is just to give you an overview of what we're going to talk about. You can actually have FPGAs that can access memory at very high bandwidth, and there's some work in this area. This is some of the work that we've done. You can offload some computation from a general purpose processor to an FPGA board, and you can specialize that computation in the FPGA and have very high bandwidth access to high bandwidth memory. So it's also another example of near memory processing today that didn't exist like 6-7 years ago. We're going to maybe talk about that. And people are actually, like big companies like Samsung and Hynix are also developing memory-centric chips. These are DRAM chips that they modify, and inside the DRAM chip they put instructions that can accelerate matrix vector multiplication and matrix multiplication. We're going to talk about that also. And these are real chips. Unfortunately, you cannot have access to this particular one, but they have results that support things. And people are also building things that look like this. This is a module that's built by Samsung and Meta, Facebook, for accelerating recommendation inference. And the idea here is you have some FPGA inside this buffer chip, and you have a lot of memory chips around it, so that the FPGA can have fast access to these memory chips and accelerate recommendation systems. Again, we're going to talk about that later on. SK Hynix has also chips to essentially accelerate similar applications. And system builders like Alibaba also have built their own DRAM chips to accelerate recommendation inference. So you're at a good time today with these different things happening, which is nice. We were talking about this starting from 2013 in these lectures, or even earlier. Now things are actually happening in industry. Okay, so, and there are more things that are happening in industry. So this is from SK Hynix, and there's also something similar from Samsung, where we have the Compute Express Link interface. It's an interface that takes a CPU and has a flexible interface to communicate with other devices as well as memory. If you have a flexible interface between the CPU and memory and storage, you can actually offload computation. And these folks have shown that you can accelerate large language models significantly, for example, by offloading computation to the memory side as opposed to doing everything on the CPU, GPU, or the accelerator. And we're going to talk about that also. So essentially the takeaway over here is we have a nice processing in memory landscape today, and there are many other experimental chips and startups that I'm not covering over here. When we talk about memory-centric computing, processing in memory, we will perhaps talk more about things. And we haven't even started specializing things for genome analysis yet. I'll probably mention some things, but as I said, this is a completely different full course that talks about genome analysis. So you can actually have devices that can sequence your DNA. This is that big, and you can actually process that information. It's not there yet. Okay, so I think hopefully I've given you some examples of these. All of these are really examples of co-design across the hierarchy. We were talking about this for a long time, but now industry is actually following this co-design across the hierarchy as well. The example that I gave you with the Tesla chip, the example that we have with Google and Amazon, etc., they're machine learning accelerators. They're really designing algorithms and the hardware together. Okay, any questions? Again, this is high-level overview. I'm taking longer than expected, actually. I should be higher bandwidth. Am I going too fast? Again, you know how to stop me. Yes, please.
Just ask a question about the startups that you mentioned. So overwhelm is a European right?
That's correct, yes.
Are there European startups that are kind of quite active in this area?
Yes, I think increasingly European startups are actually quite interesting. I think there will be a keynote tonight from Accelera. They're also doing in-memory computing, as far as I know. Don't quote me on it, so you can ask the question to the invited speaker. So essentially, there are a bunch of startups that are trying to do in-memory computing for important applications like machine learning to improve energy efficiency as well as performance. There are also startups in the US, of course, quite a few. But I'm happy that UpMem, for example, is based in France, and we've been working with them. They're in Grenoble. We've been working a lot with them on understanding the capabilities of their chips, etc. And it's not just us. More recently, all over the world, people have been using the UpMem chips to improve performance. So the best paper at HPCA 2024 this year was actually about modeling and benchmarking the UpMem chip. That's a great question. Thanks. Okay, so let me now switch gears. So that's what's happening today. These are different platforms, and we should imagine new platforms. But how do we imagine new platforms? I think we should really think about what kind of a future do we want, right? I like using this picture. This is a bridge. It looks beautiful. It's infrastructure. And bridges are infrastructure that human beings have been building for thousands of years. We've been doing computing for only 80 or so years, in the electronic form at least. We are building infrastructure that's going to be much, much more important and much, much more common than bridges. And we haven't figured out how to build bridges yet, because this is what happened to this bridge. A bit flip. Another view, and you can find videos of this online. I'm going to talk about that. And these folks, so this is essentially a robustness problem, right? How do you make our infrastructure more robust? These people are standing on another bridge, let's say. They're very happy. If a bit flip happens, in the next moment they will not be happy, right? So we're going to talk a lot about security and robustness, and this is, in my opinion, about preventing unforeseen consequences. And we should really think with this mindset, a future where we will see a lot of unforeseen consequences, because the infrastructure that we build in computing will be interacting with everything here on Earth and maybe outside in space, right? How do you make it reliable? And we're not very good at this, in my opinion, yet. That's what brings me to Mr. Bean. Mr. Bean is very happy driving his self-driving car with his whatever he's pulling over there, but he may not be very happy if a bit flip happens in this car. And then there are other things like how robust are these platforms that we want to build really? Are we really doing the right things? And we're going to talk about robustness, probably not in the next lecture, but in the next lecture, and that's going to be important. And because this is one of the critical issues, in my opinion, affecting memory, as we will see. Okay, so we want a future that's robust, in other words, reliable, secure, safe, available, etc. How do we do that? There's another problem, which is sustainability, essentially. Do we want a world that looks like this, or do we want a world where we cannot breathe in? I would pick the first one. So I think it's going to be a lot more important going into the future. We're going to talk about how to make things a lot more energy efficient and potentially sustainable. I don't want to claim a lot on sustainability, because sustainability is a term that's overused, but we will see. How do we quantify it is going to be important also. And then performance. We have a lot of difficult problems. Climate is a problem that we created as humans. We need to solve it somehow. Congestion, another problem we created perhaps. But there are other problems that we have not created. We cannot understand, like intelligence, right? What are the fundamentals of intelligence? How does it work? Can we actually really imitate it? Are the things we're doing today are really intelligent? I have a very critical view on that. I don't believe that they're truly intelligent, and partially because we don't really understand intelligence. But these are really fundamental and hard problems. And there are people in the world that are trying to solve this. And then there's a public health problem that you may have gone through in the past few years. And then there are other difficult problems that understanding genomes, for example, and doing some things with genome analysis. I'm sorry about the colors. It's kind of annoying for the eye, I think, but it's because of this conversion. My colors over here are much better. Yeah, so basically there are a lot of problems that we want to solve with genomics also. How do we develop personalized medicine so that people's lives are much better? So these are also all hard problems, and there are new genome sequencing technologies that we develop that are making it potentially easier to do these things. And we have a lot of papers on this topic. I'm going to talk about that at some point. As you can see, if you're interested in this area, so this is This is the Oxford Nanopore Technologies sequencing device. You can buy this for $1,000, and you can actually do your own, sequence your own DNA or a fish's DNA, and you can actually do a lot of analyses. I picked fish because a high school student recently used this to analyze the DNA of a fish, which is interesting. So this sort of device, and its low cost, enables people to do very different things, as you can see. And this is an area where we really need to accelerate things via, again, this full stack algorithm architecture co-design. And we have a lot of papers on this topic. If you're interested, I'd be happy to talk about it, but unfortunately we don't have time to cover genome analysis. And we have a lot of beginner readings on this. This is truly an interdisciplinary research area, genomics, as well as computer architecture. Okay, yeah, I'm going to skip some of these because we don't have time. Yeah, we have actually courses on this topic also, and workshops. And then there's the neural networks, clearly. Everybody knows about them, so I'm not going to spend a lot of time, but this is what industry has been pushing, and there's a huge compute demand and memory demand, as Kunle showed yesterday. But again, this is not the only thing. There are a lot of other forward-looking problems that we need to solve. So what's my point? Basically, we need high performance to solve all of these problems. We have a lot of tough problems at our hands, and these problems are not getting easier, and I haven't put everything over here. So we need high performance. How do we get fundamentally better performance? Are we doing the right things in our systems today to actually get fundamentally better performance? Okay, and then there's the other aspect, which is very interesting. Increasingly, we want personalized devices that we can interact more privately with. We're going to wear some of these devices, perhaps, and these devices will be interacting with us, maybe brain-machine interfaces, for example, and they're going to personalize to us. How do we do that? It's actually very common in genomics and medicine to try to do that, but we don't have a good way of doing that today. And then there's robotics, for example. How do you personalize that to a person? So this is a topic that we're not going to talk a whole lot about, but I think it's very important. How do you do personalization and privacy in every aspect of life from a computing perspective? Okay, so that's the future as I see it. You may see a different future. Just let me know if you see that different future. Maybe I'm missing something on how do we want the future to be. So if you want a future like this, then the question to ask is, what limits us in computing today? And that brings us to this course in the end. I think in general, this course and a lot of the courses that I teach are really about questioning what limits us in designing the best computing architectures for the future, and providing directions for fundamentally better designs. Hopefully we will see some of that in this course. And I will advocate some principled approaches. So for example, when we talk about memory-centric computing, the principle is really being memory-centric, doing things memory, putting memory at the, let's say, as one of the most important pieces, as opposed to being processor-centric, which is what almost everyone is doing today, right? Okay. So one of the things that we will take for granted is applications will become increasingly demanding, right? People have always had great imaginations, and as people dream, applications will come, and this will never end, in my opinion. Today, it's machine learning hype. Before, it was other things. Going forward, maybe it's going to be genomics, etc. As applications push boundaries, computing platforms will become increasingly constrained, and we will not get out of this loop. We will always want high performance. There was a time in the 1980s, for example, when people designed the it's relatively simple, by today's standards, MIPS processor. People said, oh, this is the best processor. We don't want anything else other than a 5-stage pipeline. Because this is good for performance, right? It executes everything we want to execute today. Well, guess what? People want to execute a lot more other things as well. So this will never end. So okay, what is my key realization? I think that's why we're teaching this course also. The key realization is that modern systems today are bottlenecked by data storage and movement. This was also clear in Kunle's lecture yesterday, right? If you attended the lecture, you saw that it was all about memory hierarchy and memory bandwidth and how to manage it, right? Computation, in my opinion, today is a more or less solved problem. Not exactly correct, of course, right? There's clearly specialization, etc., that we need to do. But we know how to build computing systems really, really well today in terms of how to do computation. But on the memory and storage side, we really don't know how to do very well, in my opinion. We don't know how to specialize it to different applications. We don't know how to actually use it for, in its best capability. Because memory system actually has a lot of computation capability, as we will see in the next lecture, but we're not using it at all. It's just sitting there. Whereas we bring data back and forth between the memory hierarchy and the processor, wasting a lot of energy, making our climate problem much worse, and wasting a lot of performance as well. Okay. So our focus is going to be on data storage systems, which is memory. Memory is a part of the storage hierarchy. There's clearly a storage system also. And I believe going forward, main memory and storage are going to be merged, and we need to rethink the hierarchy significantly. But let's talk about main memory. Main memory is really a critical component of all computing systems that you design today. Every system that you design today needs to have a main memory, working storage, including machine learning accelerators like you've seen yesterday. And this main memory system must scale in many dimensions in terms of its capacity, technology, efficiency, cost, and the algorithms we use to manage it. If you want to maintain performance growth and technology scaling benefits, if you want to satisfy all of those future requirements that we want. And it doesn't matter what you attach this main memory to, you're limited by it. And today we attach main memory to processors, FPGAs, GPUs, many different types of accelerators, video, machine learning, encryption, etc. Sometimes all of them at the same time, and that's why, one of the reasons why it becomes a bottleneck. Okay, so we're going to focus on memory and storage. But in the remaining part of today, let's talk about why is memory so important. I'm going to give you some data points also to just motivate you, and then we're going to go into a lot more depth tomorrow than the other lectures. But before that, any questions? Anybody wants to take any issue with what I said? No problem. We're in a scientific forum. You can take any issue as long as you can back it up with data. I'm going to back up my claims with data later on. Okay. So I'm going to give you some perspectives, like why is main memory important. I'm going to give you 4 different perspectives, well, maybe 3. Performance, energy, and robustness, essentially. Robustness is also tied with scaling, because scaling issues lead to robustness issues, but scaling itself is affecting performance and energy as well. And then we're going to cover some trends, challenges, and opportunities in memory, main memory. So this is a picture that I drew in 2008. At 2008, I was a young assistant professor at Carnegie Mellon University. I was writing proposals to the National Science Foundation. This was my career proposal, and I put this picture over there saying, this is what we have today. You have essentially a bunch of cores or accelerators, and everything else is the memory system. Basically, you have shared caches or private caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, main memory, other interconnects, and then other memories and other interconnects, etc. So essentially, the proposal that I wrote was about quality of service. When multiple applications are executing over here, how do you provide quality of service and predictability? And we did a lot of work in that area. If you took the 2013 incarnation of this course, you could actually see some of that work, and maybe in 2018 as well. But if you look at this system, most of the real estate is really dedicated to the memory hierarchy, right? Storing and moving data. Computation is a very small part of it. More than, if you actually do the calculation, more than 95% of the real estate, hardware real estate of a single node is dedicated to memory hierarchy. Okay, now let's take a step back. Assume that you're a 10-year-old kid, and I show you this picture. I have this system that I designed. 95% of my resources are dedicated to memory and storage. What do you think is the bottleneck?
But you're talking about data all the time, but most of the storage you need is for software. You're not talking about software at all, because that's the big storage area.
Yes, but software stores the data in the SSD, for example, right?
So my view is that you need a lot of memory because you are using software to enable reuse, because you have cores, and you, instead of doing things in hardware in parallel, you're trying to do it in serial, and to make it more easy to make a general hardware structure that you can reuse for many different things. Isn't it like that?
Maybe, I don't know, but I think most of the systems look like this, as I will show you in a little bit. Most of the hardware is really memory hierarchy. Computation is a very small fraction of it.
Yeah. But I would really provoke you to say that everything we can solve with a computer, you can solve in pure hardware. But it's a cost issue.
Exactly. But I'm not advocating that. I'm just basically making an observation. Most of my resources are dedicated to memory and storage. If I'm a 10-year-old, I would say, this should not be a problem, right? Because you're dedicating most of your resources. This is a solved problem, right? Yet we're still bottlenecked by memory, right? So I think this is an engineering perspective. We should be thinking as 10-year-olds maybe, and thinking, are we doing the right thing in our systems? Maybe there's a better way of designing our systems such that most of a compute chip is actually computation, and most of a memory chip, memory and computation, such that we can actually balance our resources. It's not a balanced design, I would argue. Okay, so basically the problem is today computing is bottlenecked by data, yes?
On the previous slide,
Yeah.
do you think there's also a bottleneck in the interconnect here?
Yeah, absolutely. So interconnect is part of the memory system, in my opinion. It's really about communication of data in the end, and that needs to be revisited as well.
Do you think that it's equally important to...
I don't want to go into that. In the end, depending on the workload, it may be the interconnect, it may be the memory. But in the end, it's part of the data communication. And that's why this slide comes, right? Computing is really bottlenecked by moving data around. And in fact, there was an HPCA panel in 2002. Is it the memory, is it the interconnect? Some people take sides on memory, some people take sides on interconnect. I don't want to take sides because most of memory is interconnect anyway, internally, as we will see. Yeah. Okay, so data is really key for many applications. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And data is increasing. We can generate more data than we can process, and we need to perform more sophisticated analyses on more data going into the future. So we're going to be increasingly more constrained. So there are many works, these are some references for example, that show that memory is critical for performance for different applications. Databases, graph analytics, data-centric workloads, etc. We're going to cover some of these later on. On the mobile end, we've done a lot of studies with different applications also. On the mobile end also, applications are really bottlenecked by memory. Genome analysis is another area that we've been studying, and applications are also bottlenecked by memory. In the end, scientific discovery and medical advancements are bottlenecked by memory access. And I mentioned this paper already, where we showed that there's a big memory bottleneck. This is actually a paper that we wrote in 2018 on briefing in bioinformatics, where we studied essentially all of the tools that are used commonly to do genome analysis, and we found out that most of them are bottlenecked by memory. You can take a look at that work. So let's talk about the state of the main memory system today. So we're going to cover a lot of architecture, technology, and application trends, and I've given you some trends already. These lead to new requirements, and they exacerbate some of the old requirements from the memory system. And we've always demanded a lot from the memory system, and we're going to demand a lot more going into the future. So hopefully I will show you that the main memory, the main technology that we design main memory with, DRAM, and the memory controllers, as we design them today, are unable to satisfy these requirements, and they will be even more so. And there are also some emerging memory technologies that are non-volatile that enable new opportunities. Here we're not going to talk a whole lot about the emerging memory technologies, but I think it's very important to examine emerging memory technologies, because at some point we're going to run out of steam with existing technology. That's why it's really important to look into this. So I think we need to rethink the entire main memory system to fix the issues we're having with it currently and enable some of these emerging memory technologies while satisfying all of the requirements. Now let's talk about some of these trends that I kind of foreshadowed. This is in one slide, a summary of the trends. It's not everything, but it's the most important things. Basically, we have an increasing need for memory capacity, bandwidth, quality of service, predictability, etc. And then energy and power is a big concern, and technology scaling is ending, essentially, for DRAM. So why do we need more memory capacity, bandwidth, etc.? Data-intensive applications, right? And this is not just machine learning. Machine learning was discussed yesterday. That was one of the reasons why they built this very high bandwidth memory hierarchy, right? In Kunli's chip, right? Because you need high bandwidth. But that's true for databases also. That's true for genome analysis also. Multi-core, clearly we can put many cores. Computation is not that big of a problem. We can actually put a lot of computation units if we want. The reason why we don't put that many computation units today is we know that it's going to be bottlenecked by memory. You cannot supply the data into a chip that's full of computation. You really need to orchestrate the data, and most of your chip eventually becomes caching, buffering, large amounts of caching, interconnect. There's no reason why we cannot put lots of cores onto a chip and no memory at all. But it doesn't work that way, unfortunately, because we cannot supply the data to feed that large chip. Okay, consolidation is also important. Like we want to put more applications together, and they actually demand more from the memory system if multiple applications are running. So let's take a look at an example. It's a paper from HP Labs at University of Michigan. It's from ISCA 2009, where they showed that core count is doubling approximately every 2 years. And DRAM capacity is doubling approximately every 3 years, which means that there's a gap between memory capacity and the computation, right? And this is actually increasing today, especially with accelerators, because accelerators are easier to double, if you will, because they're simpler in structures as opposed to general purpose cores. So memory capacity per core is expected to drop 30% every 2 years. This is not good, meaning that a single thread will have less performance over time. Trends are actually much worse for memory bandwidth per core. Now let me get into that a little bit. Let's talk about some fundamentals of DRAM, capacity, bandwidth, and latency. DRAM is the main memory technology that we use to design all main memories with today. I'm going to talk more about DRAM a little bit later. How many people know about DRAM here? It's dynamic random access memory. Okay, don't be shy. How many people do not know about DRAM? Nobody raised their hands. Either they're shy or yeah. But you should learn about DRAM and you will learn about it. But it's dynamic random access memory. Everybody has DRAM. My pocket has a lot of DRAM right now. This is a lot of DRAM. Let's take a look at what has happened to DRAM capacity. Well, I should have asked this question, but over the last 18 years or so until 2017. I have an updated slide I will show you in a little bit. Capacity has been improving a lot over the last 18 years. Because this is what manufacturers have been optimizing for. This is what the industry demands. We want more capacity. Bandwidth has not been improving as much. Although with recent push for HBM, high bandwidth memory, at much higher costs, you can improve bandwidth, not to the same levels of capacity. Latency has improved by 30% over these 18 years. This is because this is because of two reasons. One is focus is not on latency. In my opinion, that should change. Because latency is really important, data communication, right? If you really want to process the data quickly, you should get the data quickly, right? And the other reason is it's harder to improve. It's easier to improve capacity because technology scaling works to your favor. It's easier to improve bandwidth by paying more cost. It's a lot harder to improve latency without paying a lot of cost. So that's why when in past years we talked a lot about latency. There's still a lot of work that needs to be done in improving latency, but we're not going to talk a lot about that. Processing near memory actually reduces the latency significantly to access memory. This is the pure DRAM device. Now let's take a look at the trends from 1970 to 2024. This is one of the advantages you have taking this course. We actually did this study over the course of multiple years, analyzed a lot of data sheets, and you can find the survey. You can actually do your own data analysis if you want. From 1970 to 2024 or so, we've had more than 1 million times capacity improvement in a single DRAM chip. This is beautiful technology scaling, right? We reduced the size of a DRAM cell to store data so well, so we can pack many DRAM cells. Now let's take a look at latency. Latency doesn't look as good. Only 8x latency improvement. Again, 54 years we're looking at. And more recently, it's mostly constant, as you can see. Some latencies are actually increasing. So over the last 20 years or so, 24 years, we have not had latency improvements in DRAM. This should make you question, are we doing the right things in designing memories, right? Again, there are solutions to this problem, but I'm not going to cover them right now. But this is just to jog your thinking. Think about what we're doing in our systems today. We're improving capacity greatly, but latency is lagging a lot. Bandwidth, we figured out, oh, it's important, and we should improve it. But it comes at a cost, right? High bandwidth memory comes at a very large cost today. And it's actually, there's always a trade-off between capacity and bandwidth, as you can see, and capacity and latency as well. Okay, I've already shown you some of these. Now let me give you some data. I'm not going to give you data from my own research first, but I'm going to talk about, we've known that memory is a big problem. So this is a paper that was written by Dick Seitz. How many people know about Dick Seitz? Okay, we have a young audience. How many people know about the alpha architecture, which doesn't exist anymore? Okay, some people know, that's good. Dick Seitz was the chief architect of the alpha processors at some point, and these guys were designing some of the most beautiful and fastest processors competing with Intel at the time. And after they designed one of the flagship alpha processors, he wrote this one-page article. I would recommend you to read it. It's a microprocessor report. It basically says it's the memory stupid. It basically says, we designed this processor, it's beautiful at doing computation. It's capable of finishing 4 alpha instructions every clock cycle for a short clock cycle at the time. Unfortunately, on this important workload, it was a database workload, multiple database workloads, that we think we designed this processor for, it's finishing instructions, it's finishing 1 instruction every 4.7 clock cycles, meaning it's operating at about 5% of its peak efficiency, peak bandwidth, peak throughput. And he basically says that this is the reason is we're waiting for data to come back from memory, even though we have a complicated memory hierarchy. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And this is his sentence, is his emphasis. And I agree with that, although I'm not sure only is, only maybe a bit too strong over here. Okay, so we know that memory is a problem, but we need to change it over time. And that's why you're seeing a lot more effort today on changing memory hierarchies. Okay, this is data from my own PhD thesis, my first paper, run-ahead execution. I will briefly mention what that is about. Essentially, we worked together with Intel, and we analyzed all of their workloads that they used to design their processors with, flagship processors, and we found out essentially the same thing. Most of the time, the processor is waiting for cache misses to come back from memory. It's doing useful work only 30% of the time, or so. This is average across many workloads. And we wrote a paper, you can read it if you're interested. I'm not going to talk about it in detail, but we wrote multiple papers on this topic. And the idea over here was a processor-centric idea, although it could be applied to the memory-centric systems. Basically, instead of stalling the processor when it gets a cache miss, keep running ahead. Take a checkpoint of the state, speculatively execute instructions, and keep executing instructions that you can execute, for which you have the data for, and compute addresses that are going to miss in the caches. And this way you can start some accesses that will miss in the caches early, so that you can parallelize cache misses. I love this idea. Clearly I did a PhD thesis on this topic. I recommend doing your PhD thesis on an idea that you're really excited about. And this improved performance significantly. But it's a processor-centric idea. And this was implemented in real processors, as you can see from this talk that we delivered. Okay, so essentially memory is a problem. So, okay, if you don't believe me, you don't believe ACACES. Since everybody believes Google, Google recently published a paper, of course that's a joke, right? But Google recently published a paper in ISCA 2015, where they showed essentially the same thing. This is, according to Google, all of their data center workloads. And you can see Gmail, for example. And on a state-of-the-art Intel processor, these workloads are waiting for memory most of the time. The processor is doing useful work only 10 to 20% of the time. And they have more analysis in the paper. I recommend taking a look at it. Now again, I'll take the hat of a 10-year-old. We're doing engineering. We're designing a system. If you want to design an efficient system, the goal of the system is to finish instructions as fast as possible, right? And it's doing that job only 10 to 20% of the time. In Dick Site's case, only 5% of the time on this important workload. Is this a good system? Probably the 10-year-old would tell you the truth that they will not tell you, or that older people come to live with. They will tell you, this is a terrible system, right? I don't want this thing. I want to play with my toy that works 99% of the time, 100% of the time. Yeah, that's why we need to think as 10-year-olds. Okay, so a memory in a modern system, clearly this is, now let's take a look at real examples. This is AMD Barcelona from 2006. Cores are actually a bigger part, but there's still a lot of memory over here, memory hierarchy, as you can see. This is even earlier, Intel Pentium Pro, where L2 caches were off chip. It's good to think about history a little bit. A lot of things got integrated on chip. So this was the processor chip. Moore's law and integration of technologies enabled more memory hierarchy to come on chip, because it was important to do so. This is Pentium 4, where a good fraction of the chip is the L2 cache. This is the Apple M1, a lot of caches, etc. I didn't mark everything over here. This is AMD's one of recent flagship processors. That box over there is L2 and L3 caches. And it doesn't include all of the memory. So if you look over here, this huge box over here is the global memory interconnect. Right? And there are L1 caches over here, register files, etc. So most of the chip, compute chip, is memory. This is IBM. Again, I could keep doing this for a long time. This is a GPU. And we're adding more caches. This is 3D cache, essentially 3D stacking. As we add, these are beautiful technology. You can actually put a compute chip and something else on top of it using hybrid bonding. And AMD has been using it to add more caches. Is this the right thing to do? It's good to ask. This is an easy thing to do, but is this the right thing to do going into the future? And this is another example. I like this one because I think of this chiplet as a lot of SRAM inside, and then there's a lot of DRAM, the bigger portion, and then there's a darkness that no one thinks about, storage. We're going to talk about storage also, so it's not going to be darkness a little bit, but it's going to be important. So most of the system is really about memory in the end. Okay, since Gunli delivered this talk, I actually had to highlight his memory hierarchy over here as well. If you look at this chip, we don't have, of course, the picture of this chip internally. I believe internally it's a lot of memory also, but externally it's huge amounts of memory. And his number was not 64. This is the public version that I found. His number was 512 gigabyte high bandwidth memory. I don't know how they do that easily. It remains to be seen. Okay, so basically the point is memory system is really most of the platform in the end. Okay, so that covers the first part, let's say. The need is increasing and we're actually putting more and more memory. Are we doing it in the right way remains to be seen. Let's talk about energy. Because the first point is kind of about performance, right? Capacity, bandwidth, quality of service, it's all about performance. Energy is much worse. And this is something that no one talks about in general. But I think we should talk about it. Because this is really what is about climate, sustainability, etc. And if you look at the energy implications of putting so much memory, it's huge. This is a paper from IBM in 2003. On their big iron large-scale systems, they found out that more than 40 to 50% of the energy is spent on the off-chip memory hierarchy. This is 2003. In GPUs, again, 2010, 2015, more than 40% of the system power is in DRAM. And one of the issues with DRAM is it consumes power even when it's not used. The cell phone on my pocket right now is consuming power in memory because it's refreshing the memory because of its dynamic nature of memory. In past incarnations of this course, we used to talk a lot about refresh. Probably we're not going to talk a lot about refresh this time, but even though it's still important. Okay, let's take a look at it. So this is data that I borrowed from Bill Daly. These numbers have changed, although that 100 to 1000x remains the same today. Basically, in this picture, he shows that a 64-bit double precision floating point operation, a complicated arithmetic operation, is 20 picojoules in terms of energy. A DRAM read or write is 16 nanojoules. That's 800x difference. So maybe that's a bit extreme. If you optimize things, you get closer to 160 to 200x. Basically, a memory access consumes 160 to 200x the energy of a complex addition operation. Now the question is, does it really make sense to bring the data to the chip to do this very simple, energy-simple operation by consuming a lot of energy, right? Of course, it's a scientific question, right? An optimization question. When does it make sense to do that? It does make sense under some conditions, but those conditions require the data to be reused many times by these operations that you're doing on the data. And that many times you can calculate depending on your memory hierarchy, that many times usually tends to be thousands of times, at least hundreds of times depending on, again, cost and memory hierarchy, etc. And in many applications today, we don't have that amount of locality, like graph processing, etc. Okay. I should also say that this picture, I'm going to take a little bit more time because that's the beauty of this course, right? I got to tell you some stories. This also indicates the success of technology scaling. Meaning that this, if you go back 80 years or so, or 60 years or so, this energy differential was reversed. Memory was actually cheaper than computation. But over 6 decades of technology scaling, we've made computation much better. We were able to do Dennard scaling as well as reducing the size of things. As a result, logic became much more efficient, but interconnect did not scale very well over time. Now you're going back to interconnect as well as memory. Those things didn't scale very well. As a result, now computation is easy and cheap in terms of energy, but memory is expensive. Memory and interconnect are expensive. It's good to have that historical perspective also. We were not always like this, basically. We came to here because of the success we had in computing. But do we keep doing business as usual? Is probably something we should ask. Okay, so that was a complicated arithmetic operation. Let's look at a simpler arithmetic operation. An integer add, 32 bits still. Compare that to memory access, that's 6400x. That's a crazy number. 32 bits. No one wants to do 32 bits today. If you're following machine learning, everybody wants to do 4 bits, 3 bits, 2 bits, 1 bit, binary neural networks, right? Now multiply this by 10x as you go down. Now the memory access actually becomes much, much more costly in terms of energy compared to a 1-bit arithmetic operation. Okay, I'll give you 4 bits. A 4-bit arithmetic operation. And we're not talking about storage yet. This is just DRAM. If you want to access storage, add another order of magnitude to this. So easily we're talking about 64,000x or 100,000x differential between an access to storage. We bring the data from the storage to memory, memory to processor processor meaning caches, and then caches to the compute unit to do a very, very simple, energy simple operation. Think about that. Does it really make sense? Okay, so we did a lot of studies to quantify the effect of this data movement. This is a study that we did with Google in 2018. We analyzed those mobile workloads that I showed you earlier. I'm going to talk about this paper probably tomorrow if you have time. And we found out on average use cases, we found out that on mobile workloads like TensorFlow, for example, machine learning inference, or Chrome browsing, for example, which you may be doing, or YouTube video, more than 60% of the total system energy is spent on moving data across the memory hierarchy, from the processor to the memory. This is not the worst case. This is average. And in my opinion, this is a very underestimate of the average. So we repeated the study with Google again in 2021, this PAC 2021, and we found out that on their Edge TPU, Edge Machine Learning Accelerator, more than 90% of the total system energy is spent on memory in large machine learning models. And there are other people who have repeated similar studies. They found in some cases more than 99% of the energy spent on memory. So I'm going to talk about this probably tomorrow again, but just to give you an overview, this is from our paper. If you look at LSTMs and transducers, this is the energy breakdown with high bandwidth memory. Most of the energy is in DRAM and off-chip interconnect. So this kind of answers your question. Although it doesn't completely answer it because inside DRAM there's a lot of interconnect as well. So essentially, most of the energy is dominated by memory. But that's true for other models also, but not as much, let's say, because these are much smaller models, and people have optimized the compilers, etc., so that you can maximize locality. And locality maximization in machine learning is easier than locality maximization in many other applications like graph processing, etc. Okay, so basically we do not want to move data, I would argue, as much as possible. We want to enable computation with minimal data movement, compute where it makes sense, not restrict ourselves only to a compute unit that's far away from memory. Why don't we design compute units everywhere in the system, right? Some of them closer to memory, some of them inside the memory, some of them inside the storage, some of them on the interconnect, some of them inside the tape. Because tape is actually very important in systems because we're generating a lot of data. We cannot put all of them in SSDs. SSDs are expensive. Where do you put them? Tape sounds good. So we want to make computing architectures more data-centric, basically. So this is an example. Why don't we actually do processing everywhere over here? Why do we limit ourselves to this SRAM-dominated chip? Okay, so we're going to talk a lot about processing inside memory and storage, but just to foreshadow things, today many applications are actually stored in memory. They're in memory databases, in memory graph processing, in memory machine learning frameworks. And we want to actually offload some computation so that large amounts of data can be processed easily on the memory side. The processor says, can you execute this function for me, DRAM? And the DRAM says, yes, here are the results. There are many questions over here that we're going to cover. How do we design the memory controllers? How do we design the processor and communication units, given that this is the paradigm now, and the paradigm is not bringing everything to the processor? And when I say processor, I take a very general view of the processor. This could be a CPU, general purpose. This could be an FPGA. This could be a different accelerator, video accelerator, machine learning accelerator. This could be a GPU. Basically, for me, all of them are processors. How do you design the software and hardware interfaces to enable this? How do you design the system software compilers and languages to enable this? How do you design the algorithms to take advantage of the substrate on the memory side? I'm going to talk about theoretical foundations later on, but this is really an across-the-stack problem. That's one of the reasons why we're going to dedicate a good chunk of this course to memory-centric computing. But I'm foreshadowing this right now. In my opinion, memory-centric computing can improve all of these, but most importantly, perhaps energy. Even though you may not gain performance with memory-centric computing, you will gain energy because you're not moving data as much. And we've shown this in many cases. You gain performance and energy, actually, in most cases. But when you don't gain performance, you actually gain energy. Well, gain energy meaning you reduce the energy consumption. Okay, any questions? I know I covered a lot. Yes? I cannot hear you very well. I don't know what's the solution to this. Does this work?
Teacher.
Yes.
You must repeat the...
Yeah, but I cannot hear the question.
Okay.
Yes, loudly.
So if you are trying to implement the system using like a data-intensive application,
yeah.
which one should we care more about, latency or the
It depends. It really depends on the application. We're going to talk about that in later lectures, but different applications have different bottlenecks. Some of them are bottlenecked by bandwidth, some of them are bottlenecked by latency. Usually complex applications are bottlenecked by both at different times. And then there's the capacity also.
For example, if you were trying to do like machine training, any idea which one to repair?
Again, it depends. I mean, once you solve some of the problems, it becomes latency bound also, right? You can actually transform one problem to another. Yes?
Yeah, so one of the causes of the memory power consumption issue isn't that the data set is bigger than the cache size, and so the cache doesn't work anymore.
In processor-centric systems, yes, that's one of the causes, yes. But if you change it to a more memory-centric system, yeah. Basically, okay, repeating the question, well, the first question was, is the application bottlenecked by bandwidth or latency? And my answer was both, depending on the application and depending on the time. And the second question was, one of the causes for the large power consumption of memory is because the cache doesn't fit the data. And the answer is yes, that's part of the cause. But if you change the paradigm to be more memory-centric, if you execute things on the storage side where you don't have this problem, you don't have this problem essentially. Okay, so let me cover in the remaining time DRAM technology scaling, because it's actually going to be important, because DRAM technology scaling, meaning reducing the size of the DRAM cell, making it more efficient, making it higher capacity, has enabled a lot of improvements. That's why we're trying to put 1.5 terabytes or many, many terabytes of memory, right? Unfortunately, it's not going well. Scaling has provided higher capacity, lower cost, lower energy, and difficulties in scaling. That means that if DRAM doesn't scale, we're not going to sustain those performance benefits. And also, it creates robustness problems, as we will see. Okay, so we've been writing a lot of papers. We've been working on memory for a long time, but this is a paper that we delivered at an industry-dominated conference, International Memory Workshop. They invited us, and we argued that we should really rethink how we design memory, and we should really take a systems architecture perspective. We should not say memory should be designed by the manufacturer and we should forget about it. We should really make the memory work together with the entire system so that we can scale the entire system as opposed to trying to scale memory itself. This will become more clear, hopefully. So what's the DRAM scaling problem? So if you look at DRAM, you need to store 1 bit. That is stored in the capacitor as charge. Charge versus discharge indicates 1 bit storage. And then you need to have an access transistor to access the data, and the bit line to perturb, and then the sense amplifier to sense the data. So this is the basics, basically. We're going to talk more about that later on. But for this to work, the capacitor must be reliable. The access transistor and the sense amplification circuitry must be reliable. Now, as you reduce the size of the circuit to pack more cells in a given hardware area, both of these properties become difficult to maintain. There becomes a lot of noise in all of these structures. And in 2009, ITRS was suggesting that reducing the size of the circuitry below a feature size of 35 nanometers is challenging. Today, we're very close to 10 nanometer in DRAM. That doesn't mean that they were wrong. It has been challenging, and we've seen a lot of problems with DRAM, as we will see in a little bit. Okay, so manufacturers have been actually doing a lot of heroic acts. So this is what DRAM looks like internally. So this is a capacitor. They've etched the capacitor into the substrate. The length of this capacitor is maybe 70 to 80 times the length of this transistor over here. So this is another view, basically. That logical view that I showed you was very different from the real physical view. This is the transistor over here, access transistor. This is the capacitor, and then there's a bit line and the word line to access. Again, I don't want to go through this in detail, but manufacturing has become much more complicated, and DRAM manufacturing is a very tough area. So I have a lot of respect for people who manufacture DRAM. It's a lot harder than manufacturing processors, in my opinion, today. But it's not going well either. Okay, so this is a general problem with charge memory in general, meaning when we actually store data in terms of charge, in a capacitor, for example, it becomes difficult to place and control charge because electrons escape. They go to different places, basically, if they're kind of confined to a very small area. In Flash, we store data in floating gates. In DRAM, we store data in capacitor. And data retention and reliable sensing becomes difficult as this charge storage unit size reduces. So we are seeing similar issues with flash memory also, but I'm not going to talk about that flash memory as much. So one of the problems is, as we reduce the size of each memory cell, it becomes less reliable. So this is a study that we did with Facebook. We published in 2015. We studied all of the memory in all of their data centers, all of the memory areas. There's a lot of servers, even at that time. They didn't allow us to publish how much memory, how many servers, because they thought it would affect their stock price, etc. They should be more concerned about other things, in my opinion. But this is really statistically significant. And this is one of the plots. Basically, this is production data center servers. We didn't, everything is running on Facebook. We're examining memory errors. So we see more memory errors, more server failures on servers that have DRAM chips that are less dense, 1 gigabit. And memory errors increase, or server failures increase, if you're employing chips that are much denser. This is because denser chips have smaller cells and cells that are packed closer, so they're much more vulnerable to noise. And if you're interested in this, more is in the paper. We have a lot more data in the paper, including solutions to the problem. So we built a lot of infrastructure to understand these issues. We built FPGA-based infrastructures, FPGA-based memory controllers, soft memory controllers to test DRAM. And these are some of the papers. We're going to talk about this more. And these are some examples. If you're interested, you can actually use some of these. We release it as SoftMC, but more recently, you're lucky right now, we released a much better version of it. It's called DRAM Bender. It's a lot easier to program. If you have an FPGA, you can actually download our program and test memory chips. And this is a very interesting research area today. And these are different FPGAs that we support, and the paper is over there. So one of the reasons why we actually built this was to study data retention issues in memory. As I said, DRAM, over time, capacitor leaks, it loses charge, and you need to refresh DRAM periodically. So my computer, my cell phone is doing that right now. It's in self-refresh mode, it's refreshing memory, so that it doesn't lose the data. So we wanted to, this is a scaling problem actually. As you reduce the size of the cell, this becomes much worse. So refresh rates 10 years ago were less frequent than today. Today refresh rates are every 32 milliseconds you refresh all of the cells. But when we first started doing this, it was 64 milliseconds. So we asked the question, can we get rid of refresh as much as possible? And this is what we did. Essentially, we realized most of the cells don't need to be refreshed often because they're actually strong enough to keep the data longer than 64 milliseconds. Why? Because there's process manufacturing variation that happens. Everything is about variation, right? Humans actually have variation also. Genetic variation is there. Everything that's manufactured has a lot of variation as well. And this is a variation inside a chip. Most of the cells can retain data for 260 milliseconds. Now, if you can figure this out by testing the DRAM chip online or offline, you can actually get rid of most of the refreshes, more than 75% of the refreshes according to this picture. Now, this turned out it's not that easy. You need to identify this for every single cell, and this is dependent on the data values of the cells, and this is also dependent on some quantum-like effects, especially when you scale the technology to smaller nodes. It becomes random. A cell changes its retention time randomly, and you need to account for that. So we wrote a lot of papers on this topic that I'm not going to cover. If you're interested in this, go back to the 2018 and 2013 lectures, but I think this is still a fundamental problem. I'm just going to flash some of these papers. This is a paper that's actually quite interesting. This is the paper where we actually showed real results from our real infrastructure. You can take a look at that. And these are some papers that we keep writing. If you're interested, I'd be happy to talk about it, but unfortunately, we don't have time. Okay, but what we're going to talk about is other issues that are actually quite interesting also. And one issue is the row hammer problem. How many people know about the row hammer problem here? Okay, I see a lot of hands. How many people do not know about it? Okay, that's good. I see quite a few hands, so you'll learn in this lecture. I talked about this in 2018, and I said that this is a big issue. And it's a much bigger issue today, basically, as we will see. But let me give you the idea. Essentially, the problem is these are DRAM chips, and you can predictably induce bit flips in them. This should not be happening. Nobody should be inducing data corruption in your DRAM chip. And as a result, this becomes a security problem also. This is a hardware failure mechanism that exists in DRAM chips, and all the recent DRAM chips are fundamentally vulnerable. And people have exploited this vulnerability to launch attacks. And we will talk about that when we talk about memory robustness. And you can see articles that people are writing, forget software, now hackers are exploiting physics. I like this one. People should think more about hardware. In fact, I will also tell you some stories about the security community. Like, I've been working on hardware security for some time. Our first paper was in Unix security in 2007. We may be only hardware security paper. In fact, my session was titled Low Level. Now, if you look at Unix security 2024, 17 years later, there's a full track on hardware security. And one of the sessions is row hammer. I think there are five papers on that topic. So security as community has evolved, and seeing that hardware is actually a lot of security issues, and that's becoming important. So a good chunk of the security community is actually working on hardware security today. I'll probably show you next. But this is our paper. I'm not going to talk about that right now. But these are actually robustness issues, essentially. Robustness is a big problem today in memory. Refresh, row hammer, other types of disturbance issues that we will talk about, and other types of bit flips. Okay. I will quickly finish it, and then we'll go for the break. But there are other major trends also. Essentially, because scaling has become difficult, people have started developing emerging memory technologies. 3D stacked DRAM was developed to provide higher bandwidth. Unfortunately, it comes at cost. Reduced latency DRAM was developed to provide lower latency. Low power DRAM was for low power. Non-volatile memories, of which there are many kinds, were developed to provide larger capacity in general to overcome the scaling problems. Unfortunately, there is no memory that's good at everything. As you can see, there are downsides to every single memory. But increasingly, we're going to see more of this into the future. We're going to see a lot of proliferation in the memory space. Memories will be more specialized to the application, in my opinion, also. This is what we've been arguing for a long time. I believe it's going to happen sometime soon. But one of the major trends that this has enabled is we have hybrid main memories today. Essentially, you may have some technology that's good at some things, that's bad at some things, and then some other technology that's good at some other things and that's bad at potentially complementary things, right? And you put them together and design the hardware and software to manage the data allocation and movement to achieve the greens of each technology as much as possible while avoiding the reds of each technology. And we envisioned this a while ago. This is DRAM, this is phase change memory. But this could be different types of DRAM, right? This could be high bandwidth DRAM on the left and large capacity DRAM on the right, as people are doing today. Most people are doing that today. But I think this is going to proliferate more and more. So if you want to design something like this, you really need intelligent memory controllers to manage things. So I think this is going to be important. So why do you need intelligent memory controllers? Because intelligent memory controllers need to recognize the different devices, recognize their upsides and downsides, and recognize the requests coming from different applications and match the right type of memory to right type of application and right type of request, right type of data structures. I think this is fascinating. This is an important problem, and we haven't solved this problem yet, in my opinion. Okay. So I should also mention that industry is writing papers about it. This is a beautiful paper that was written by Samsung and Intel. This is the only paper that I know of Samsung and Intel wrote together. These companies don't normally talk to each other. Actually, Samsung doesn't talk with anyone else. I'm just joking. But basically, unless there are armies of lawyers on either side, they don't talk to each other. But these people found that DRAM technology scaling is so difficult that we really need to write a paper about it. And in 2014, they wrote a paper where they basically said some of the things that we've been saying. Refresh is a problem, write latency is a problem, etc. So we really need to design intelligent memory controllers, design memory and the controllers together to overcome these problems. And this is going to be a theme that we will see in these lectures. We're going to cover the rest of the slides, some of them, tomorrow, and we're going to jump into memory-centric computing.